So, I hope you have enjoyed the experiment in the previous lecture. We implemented the circuit which is on the board, and we showed you how that cutoff region, that active region and saturation regions appear as you increase this voltage. Now, this active region is related to the amplification action, and here is the relation, and it has to be in this linear region, and then the voltage gain is given by that beta factor of the transistor, and then multiplied by this RL and divided by this RB. This is RB. So, today I will again go to that same experimental setup. It is still there on the table, and we will explore more on this linear region. In this linear region or this active region, I will be varying this input voltage which is given to this base circuit little bit by just varying this variable contact here, and then slowly we will increase or decrease, we will change this Vi, and we will calculate what is the change delta Vi or delta Vs. So, that will be the change in this input voltage which will represent signal, change in that signal voltage, and then we will measure the change in this output voltage, and we will calculate this delta Vo divided by delta Vi. So, this experiment once again we will be doing, and we will see that how this ratio, whether it is constant in this active region or how does it changes, and then we will try to calculate beta of this transistor from our own observations. So, that is the agenda today. So, let me make a table to write the values, the data, and we will have a column for the input voltage, Vi. So, different input voltages we will write here, and then this column I am leaving here. This column is for delta of Vi, which is same as delta of Vs, right. Whatever change in the input voltage, that is the change in that signal, because VBB is always fixed in a given circuit. So, this will be here. Similarly, output Vo, that we will write here, and then we will see how that output voltage changes. That will be delta V0, and then this will be our voltage gain, that is delta Vo divided by delta Vi, that is this voltage gain. So, different readings we will note in different rows. So, let us take 1, 2, 3, 4, 5, 6 to get the idea that how that it changes. Okay. So, I will be doing the experiment, and on the two multimeters you will have this Vi and Vo, and then I will ask Mr. Ranjit to fill this table as I will call the numbers from the experimental table. So, you have the same circuit which we used in the previous lecture. Here is that transistor, and then all that collector, base, emitter, everything is same. That circuit is connected as such. This battery switch is open here. When we will connect it, that input biasing circuit will be on, and of course, this variable voltage I have to put at different places. Then the positive of the battery, this is also open here. So, when we will connect this, then that 9 volt will be applied to that 10 kilo ohm resistor, and from there it will go to the collector. So, the entire circuit is the same. So, let me connect it, and I am putting this thing here. So, now this battery, this cell voltage is falling on this whole coil, whole conductor here, and the positive I am connecting here. So, the circuit is complete. For measurement, we have to put on the multimeters. This is to read that input voltage supplied, and this will be in the range of 2 volts. Since I have not connected, it is not showing anything here. To measure that output voltage, we will be putting this one at 20 volt range, and you can see it is already reading that voltage there. So, let us start taking measurements. Ranjit, you will be writing on the board. We have already drawn the table for you. In the first column, you will be writing the input voltage, and in the third column, you will be writing the output voltage. We want to be in the active region, linear region, to see that amplification thing. So, let me give this biasing voltage somewhere here, and you see the output voltage is hardly decreases, 9.26. I am not in the linear region. I am close to the end of the cutoff region, where the curve has started curving. Actually, initially it is flat, and after that it curves, and then it becomes linear, it decreases. So, I am in that curved region. So, let me give some more biasing voltage. Yeah, input 0.746, output 5.68. Zero 0.767 and 5.22. Zero 0.799, 4.54, input 0.821, output 4.07. Input 0.842, output 3.61. Input 0.857, output 3.29. Input 0.875, output 2.89. Zero 0.897, 2.41. Zero 0.916 and 2.00. Okay. So, we will stop here, and all these data have been noted on the board, and we will do the analysis. So, thank you Ranjit for writing this data. So, these are the input voltages Vi, and these are the corresponding output voltages. So, let me see what is this delta Vi. So, first I will subtract this from this. So, I have increased this Vi by how much amount? So, this is 1 here and 2 here and 0 here. So, I have increased this Vi by this much amount. I have subtracted this from this, right. Similarly, if I go here, I have increased it by how much amount? 2 here, 3 here, 0 here. Then it is 2 here, 2 here and 0 here. Then it is 1 here, 2 here, 0 here. Then it is 5 here, 1 here and 0 here. Then it is 8 here, 1 here and 0 here. And here it is 2 and 2 and 0. And here it is 9 and 1 and 0. Please check, please verify if this subtraction is correct. Okay, this minus this should be here, this minus this should be here, and so on. Similar thing we have to do here. This is delta VO. So I have to see how much this VO has decreased. So I have to subtract this from this from this, and so on. So let me fill this column. So I have to subtract this from this. So 8 minus 2 is 6. Then here it is 6 minus 2 is 4. Here it is 12 minus 4 is 8 and 11 minus 5 is 6. Here it is 14 minus 7 is 7 and 4 minus 0 is 4. Here it is 7 minus 1 is 6 and 10 minus 6 is 4. Then here it is 11 minus 2 is 9 and 5 minus 2 is 3. Then here it is 9 minus 9 is 0 and 12 minus 8 is 4. Then here it is 9 minus 1 is 8 and 8 minus 4 is 4, and then it is 1 minus 0 is 1 and 4 minus 0 is 4. Okay. So this is delta VO. And now I have to take ratio, delta VO divided by delta VI. So this divided by this. So let me take my calculator and do the calculations. Alright, so delta VO is 0.46. So 0.46 divided by 0.021, 0.021 equal to, this is 21.9. This is 21.9. Then 0.68, 0.68 divided by 0.68 divided by 0.032, so 0.032, and that turns out to be 21.2. 21.2. 0.47, 0.47 divided by 0.022, so 0.022, and that is 21.4, so 21.4. Then 0.46, 0.46 divided by 0.021, 0.021, and that is 21.9, so this is 21.9. Then 0.32, 0.32 divided by 0.015, 0.015, and that is 21.3. This is 21.3. 0.40, 0.40, and that divided by 0.018, so 0.018, and that is 22.2, 22.2. Then we have a 0.48, 0.48 divided by, and this is 0.022, so 0.022, and that is 21.8, 21.8. You have 0.41, so 0.41, and then divided by 0.019, 0.019, and that is 21.6, 21.6. All right. So you see, it's very linear. Delta VO by delta VI is almost constant. It's almost constant. It's between 21 and 22. And remember, each measurement has a least count. When I write this 746, this last digit here is least significant. So there is an error of 0.001 here, there could be an error of 0.001 here, and when you are subtracting, the errors add, so it can be an error of 0.002 here, and an error of 0.002 is not small because this whole number is 0.021. and if the error is 0.002, that means error is 2 in 21 is 10%. So there could be a 10% error here. So this is the scenario, and similarly there can be an error of 0.02 here, but that error will be small because it is in 0.46. You have that error of 0.02 here, that is small, but here that error can be very large. For example, in this it could be 10%, up to 10%. Here it will be less, it is 2 in 32, so about 6%, and so on. So there is error involved because of this. When I am reading from the multimeter, this last digit is always a doubtful digit, and therefore there is an excellent constancy of this ratio, and you have a really flat region in that VOVI diagram. So here the voltage gain is, let us take some average. I will not calculate the average. What should be the average? Somewhere around, let's say, 21.5. So this is delta VO over delta VI. This is, let us take 21.5, and this is equal to, remember we are taking magnitudes, this is beta times RL over RB, and this is beta times RL. What was RL? Remember in the circuit, what was RL? On the collector side we had added 10 kilo ohms. So this is 10 kilo ohms, and on the base we had added 120 kilo ohms. So this is 120. So your beta is 12 into 21.5. Can you work out without calculator? 12 into 5 is 60, so 6 here, 12 and 6 is 18, and 24 plus 1 is 25. So that is the beta from our observations. That is how the amplification works. I have shown you the amplifying action. In a real amplifier, you will have many more things. You will have a lot of capacitors for filtering and other things, and then the signal will be some kind of a fluctuation on the average VBB. I have taken a gradually increasing signal. Signals are not like that. So all those things are there, but that basic amplification by the transistor, that you must have felt through this data. Okay, now the next topic that we will be taking is transistor as a switch. The job of switch is to put a circuit off or on. Now, why I need a transistor in place of just a switch? We have so many switches in our household. For each bulb, for each fan, we have a switch, and we do not put any transistors there. So what's the benefit of putting transistors and how it works? The benefit is, as you know, in the transistor circuit you have two parts. One is input part, one is output part. Now this output part, the current is higher. You have a current gain, beta times more current there. Beta is 200, then 200 times more current is there. Input side is a low current part. The current that goes through the base part, that IB, is still a few tens of microamperes, whereas that in that output part, collector part, that could be 200 times more. So when we use transistor as a switch, what we do is we control this output circuit through this input. You have already seen the cutoff region, the saturation region. So if somehow I decrease my VBB, the biasing voltage that I am applying on the input side, transistor will go in cutoff region. So cutoff region, there is no currents anywhere, and at the output you have a full battery voltage VCC that appears there. So decrease this VBB to a small value, and you have output there, large output there, and then increase this so that it goes in saturation. So increase this current here, IB here, increase that VBB there, and what you have is very small output voltage. So that output voltage can be switched, right, can be switched from high value VO, which can be VCC, to a very small value by controlling this VBB here. So what you are doing is you are controlling a large current circuit through a small current circuit. You are actually doing switching. You are actually doing switching in that base circuit, that VBB, that forward bias of base emitter junction. You are switching there. You are somehow changing that voltage to a low value to a high value, right? The voltage that you apply to that base circuit, you change it from a high value to a low value, from a low value to a high value. That is the switching. So you are switching in the base circuit, and what we are controlling, the output. So there the switching is appearing there. You are doing something here and the result is appearing there. So you are controlling a high current circuit from a low current circuit, and that is the benefit. That is how that switching takes place, and that is why transistor is used for switching. And in digital electronics, the switching from high value to low value at a faster speed is very, very important, and all these things make transistor a useful device for switch. So the circuit of transistor as a switch will be same as this common emitter thing that we had done. Let me draw it again. So you have that transistor, and then emitter is grounded, and on the base side you have your controls here. So you have some resistance, and after that you have some kind of, let me first put a switch here like this. This is the battery, biasing battery, and then there is a switch out here. And on the collector side you have some load, maybe some kind of a lamp or something else. You can still have a resistance, and then you can have your biasing battery like this. So here is the control, and if the switch is open, this is in cutoff mode. There is no biasing there. Since there is no biasing, no current, and therefore no current from here also. So this IC is also 0. Okay, this IB is here. If IB is 0, then IC is also 0. This is IE. And if you think of this VO here, VO, then you are in this region. You are here. VI is 0 and VO is maximum. Whatever is voltage here, that appears here. You are in the cutoff region. And suppose suddenly you switch it on. Suddenly you switch it on. You connect this, so that now you have a biasing voltage, and this is sufficient to forward bias it. Then what will happen? You have the current, you have this IC, and large IC, saturation range. This is sufficient here to drive this into saturation region. So in general we have VO, VI like this. So you are here and suddenly you reach here. So your VI is sufficient, this is sufficient. So we are operating in the cutoff region and saturation region, then it becomes a switch, right? So if you are not providing the current here, then there is no current here and this voltage is maximum. And if you are providing sufficient biasing here, then you have sufficient current here, large current here, and then this is almost 0 that we had seen. So this is how it works as a switch. So it is switching this circuit. The only important thing is it is switching this circuit, although I am putting the switch here. So this is that low current part in which I am operating, and I am controlling a larger current part. So I will show you an experiment here on this table. And the another interesting thing is, You don't have to connect a real battery here. Any kind of voltage control, if you can have here, which can drive this biasing from almost 0 to a large value, then you are done. So what we will do, we will put a solar panel here. We will put a solar panel here. Okay, so we will put a solar panel here, and then when light falls on it, the voltage is generated, and if this light is off, then this is also no voltage here. So just by controlling the light here, you can control this part of the circuit. So let me show you on the table how this circuit is implemented and how a voltage here or light here can control this appliance here. So I have already connected the circuit. This is a solar panel on which some light is falling, and it is being used in a biasing circuit of the base part. I will just show you that. And on the collector side, I have used this bell here, electric bell here, and of course the resistances will be there. We will be controlling this bell, this circuit which is in the collector part, which needs sizable current through this base part. So let me show you the circuit once again. So what you have here is on that same breadboard, similar circuit that we had shown earlier. You have this transistor, this is the flat surface here, and this is the collector, this is base, and this is emitter, and this emitter is already connected to this ground line. This is my ground line. So emitter is grounded. From the base you can see you have a resistance here. This resistance is 10K resistance, and then from here I am coming to this line, this line, this line, this line here in this hole, that second line from the edge, this one, and this one we will be connecting to this wire, and this wire will be connected to the positive from the solar panel. So I have this solar panel, and the positive of the solar panel is here. So if I connect it here, then this base circuit is connected, all right, and the negative of the solar panel is connected here. This is that negative here, this is that negative here of the solar panel. So that will be connected here. So let me connect that. So negative is already connected, and positive we will connect after describing the circuit. So on the collector part, you can see here is the collector, this is the collector. When the flat part is facing you, the left side is collector, and on the same row I have this resistance, I have this 1K resistance, and 1K resistance comes here, and then in the same line I have this red wire, and this red wire is going into this bell. This red wire is going into the bell, and from the bell we are coming back, and that is connected here. This is connected here, and this is the last line, this near the edge, and this is connected here, and this we will be putting the 9 volt biasing. This 9 volt biasing we will be putting here. So here the collector circuit is complete. Okay, so you can compare with the circuit that is drawn on the board, and we will be adding this plus here. And you see the bell is ringing. You can see this. You can listen the sound, and perhaps you can also see the flickering of light here in the bell. And now I am going to stop this voltage here, the solar panel, the light falling on the solar panel. Gone. The bell is not ringing, and when I allow the light to fall, bell rings. So I am controlling that electric bell from this light falling on the panel, which is in the base circuit and which draws very, very small current. That is how a transistor is used as a switch.